Hello, and welcome to Mr. Ambrose's video on proving the limit comparison test. In order to do this, we first have to revisit the limit and a more formal definition for a limit. And what you see on this page here is actually that formal definition. So this here says that if we take the limit of f of x as x is approaching a, if the limit exists, it equals some number, and in this definition here, we're going to call that number L. So by definition, this limit exists if someone else were to, say, throw at us or provide any particular number that's positive, and we call this number epsilon. Regardless of what that number might be and how small it even might be, what we would have to do is we would have to provide, or there would have to exist, another number, delta, such that if we consider the difference between the function f of x and the value of the limit, that difference in absolute value is less than that number epsilon which is being provided to us, right? That actually can occur if we can, again, choose the value of delta such that if we take the difference between x and a, and that's coming from our definition, from our limit, if we take that difference, the absolute value of that difference is less than the delta that we would have to provide. Now, this again is a very challenging, difficult definition of our limit. It's the formal one, but it is difficult to understand. So to perhaps help further understand it, let's take a look at this particular demonstration here. What you see on the screen, we have a limit, the limit of 2x as x approaches 2. The way that we've evaluated limits all year long, right, we could just, if we plugged in 2 into this f of x expression, we would get 4, which is the value of this particular limit. Now, how does this work? Why does this limit exist and equal to 4 under the definition I just showed you? Well, what you see here on the left is this Mr. Ponderin face, and he says that I believe that the limit is true if you can show me some neighborhood around a equals to 2, that's our x value, right? And we have to come up with the neighborhood where every x produces a y value within 1 unit of 4. 1 unit, that 1, is our epsilon that is being provided to us. We have to demonstrate that we can come within 1 unit of 4. And what you see here, we have the graph of y equals to 2x, and we see that and if we go 1 away from 4, that would take us down to 3 or up to 5. And we see that there definitely are functional values where that actually occurs, that we're within 1 of 4. And in order to make sure we're in that range, if we go, as Mr. Einstein says here, if we choose delta to be 0.5, right, if we go down to 1.5 or x equals to 2.5, within that interval, we definitely get values that if we take 2x and subtract it from 4, we are within 1 of the limit of 4. And the idea is that, again, epsilon is some particular number, and no matter how low someone gives us a number, they could really challenge us and perhaps move it down to, say, about 0.1. We can still produce a neighborhood where all the f of x, or the 2x in this case, minus 4 values are within that 0.1 epsilon provided value. So this is the basic idea of that definition, and this is going to come into play as I perhaps try to prove the limit comparison test. Okay, so now that we perhaps have a better understanding of this limit, let's actually take a look at our limit comparison test. You saw on Friday that with this particular test, we're given 2 things. One, we have 2 series that both series have only positive terms, right? This is important. You can only apply the limit comparison test when you have only positive terms in your series. And the second thing is we're given that we take the limit of the ratio of those general terms as n approaches infinity, and we get an actual number L where L is not 0 and a positive value, right? So L is some positive number. If that's the case, then the conclusion we can make is that both series will either converge or both series will diverge. The limit comparison test is similar to the comparison test in the fact that when you're working on a question, you have a series, right? You're going to select your twin series, and then basically, like the comparison test, if you do this limit evaluation, you get a value of L. Whatever your twin series does, so will your series do, right? Meaning that if the twin series converges, your series converges, or if your twin series diverges, your series you're examining diverges. Okay, so to prove this, I'm going to start off using this particular limit, and so we'll start there. We know that the limit of the ratio of a sub n over b sub n actually exists, right, as n approaches infinity. Now, this is going to be a little bit different than the definition I just gave to you for the limit, in the fact that infinity isn't a real number, so when we have this type of limit, basically we have to find a value of epsilon, or if we're provided a value of epsilon, we have to find the delta such that we're within epsilon of the limit for n values starting off at like a large number, say like 1,000 or 10,000 or 1,000,000, and greater, where again this functional value a sub n over b sub n minus L is within epsilon. Okay, so since the limit exists, we already know that that actually occurs, right? The limit exists. That means that a sub n over b sub n, our function of value, minus the value of the limit L in absolute value, this has to be less than our epsilon, right? That has to be true to satisfy the definition of the limit. Now, again, we're usually provided the value for epsilon that we have to demonstrate that this is true for. But for this particular proof, I'm going to say that epsilon is a number, and in this case, I'm going to call it the number L over 2. All right. So with that being said, I'm going to do some algebra to perhaps rearrange this particular inequality. First thing is I'm going to get rid of the absolute value, so that would mean that negative epsilon would have to be less than a sub n over b sub n minus L, and that would have to be less than epsilon. The next thing I'm going to do actually now is, because I'm saying that we're going to let epsilon be equal to L over 2, it's just a particular value, but if that's the case, then I'll substitute that in, and we'll have negative L over 2 has to be less than a sub n over b sub n minus L, which would have to be less than L over 2. And then we could perhaps add L to all sides of the inequality. When I add L to this left side of the inequality, I will get just L over 2. When I add that to the inequality in the middle, or the interval in the middle, we just are left with a sub n over b sub n. And then when I add L to the right-hand side of our inequality, we'll get 3L over 2. And last thing algebraically I'll do here perhaps is I will multiply each interval of this inequality by b sub n. And I don't have to worry about the inequality flipping here, because remember, another condition of the limit comparison test is that b sub n, the terms of b sub n, have to be positive. So our inequality, the less than symbols will stay as is. We don't have to worry about flipping them at all, because b sub n will never be negative. And when that occurs, we now have this particular inequality. And it's this particular inequality that we'll now use to help finish off this particular proof. And so if I can copy this, I'm not going to be able to copy it. All right, I'm going to go to the next page here. So we have here that L over 2 times B sub n is less than A sub n, which is less than 3L over 2 B sub n. And now I'm going to apply the comparison test to help show that the limit comparison test actually works. And the focus is going to be on A sub n sort of being our twin series in this case. It doesn't technically matter which way we set up our ratio when we evaluate the limit comparison test, but for this here, we're going to say we're comparing to A sub n. So, if we know that A sub n, our twin series, converges, right? Well, the way that this inequality is set up by the comparison test, since everything in L over 2 times B sub n, or that expression is always going to be less than A sub n, that would mean that the series with general term of L over 2 B sub n, right, that series would have to converge because every single term of this particular series is less than the respective term in the series with general term of A sub n. So this particular series has to converge by the comparison test. Well, if L over 2 times B sub n, that general term there of the series, converges, then that means that the series with general term of just B sub n has to converge, right? Because we also saw another theorem that basically says that multiplying by a non-zero constant does not affect overall convergence or divergence of a series. So this series has to converge. So this demonstrates that both series converge. And then on the flip side, let's assume or say that what if the series with general term of A sub n diverges? Well, if that's the case, then we can look at the inequality on the right. If the series with general term of A sub n diverges, that means that since 3L over 2 times B sub n is greater than A sub n, the series with general term of 3L over 2 times B sub n, that series has to diverge. Again, by the comparison test, right? Every single term is greater. That means that this series here has to diverge. And if that series has to diverge, then the series with general term of B sub n also has to diverge, once again because of the fact that multiplying a series by a non-zero constant does not affect overall divergence of a particular series. So this in particular proves our limit comparison test. And again, the basic idea is that if you perform the limit of the ratio of the general terms as that approaches infinity, and you get a limit value that is a positive constant, then your series you're testing will do exactly what your twin series does. And it doesn't technically really matter where you place the twin series in this ratio, whether you put it in the numerator or over the denominator. This particular test works. So hopefully that helped. Helps you understand the limit comparison test, and I hope that you have a great weekend. Take care.